All right, so that's how you use parallel axis theorem. As long as you know the area moment of inertia about one axis, you know the area of the surface, and you know the distance between parallel axes, you can find the moment of inertia about one, knowing the moment of inertia about the other one. Right? Now let's see how can we use parallel axis theorem and the information about moments of inertia for surfaces, simple shapes, simple surfaces, to find the moment of inertia values for composite areas. Right? Let's first take a look at the tables. I'm going to bring them from. So these are the tables from table 1. It could come as a bigger table. There we go, table 1, and then table 2. All right. These are tables from, let me write it here, page, I think it's a figure 912, page 499. Tables from textbook, figure 12, page 499. All right. Now let's see, what do they tell us? It's just one table. I broke it into two pieces so I can fit it in this slide. If you look at your textbook, it's just one table, long table. So different. These are simple shapes, right? So let's just start with the rectangle. We should have put probably this one on the left. So the rectangle values for rectangle, we are given area moment of inertia about x and y. Right? This is area moment of inertia about x, or moment of inertia about x. This is moment of inertia about y. Right? Knowing b and h, 1/3bh cubed. I about y is 1/3hb cubed. We're also given area moment of inertia about x prime and y prime, axes passing through the center of the area. 1/12 hb cubed, 1/12 bh cubed, depending on which direction you are finding the moment of inertia. And this is what we actually calculate ourselves. Knowing one, we could calculate the other one. Here in this table, they all are listed. And you're also given the polar moment of inertia. If this is like this distance is square root of b squared plus h squared. And that would be the distance. Then knowing the distance, this is going to be your polar area moment of inertia, polar moment of inertia. For a triangle with BH about, this is polar, this is polar moment of inertia about the centroid. So you don't even need the distance. It's about the center of the area, right? So for triangle, you're given a pretty good set of all the information for the simple shape. For rectangle, today, and triangle and rectangle. So triangle, actually triangle, Ix, or moment of inertia about x, and by x I mean the axis on the base of the triangle. The area moment of inertia, or moment of inertia about that axis, is 1/12 bh cubed. And the moment of inertia about the axis parallel to the axis passing through the base, the axis passing, let's put it this way, the axis passing through the center of the area of this triangle, parallel to the axis passing through the base, is 1/36 bh cubed. Right? And the same story, if you keep going for a circle, you have Ix bar, Iy bar, meaning that x and y axis passing through the center of this circle. The area moment of inertia is 1/4 pi r to 4. And you also have the polar moment of inertia, about the center. About the center. You get area moment of inertia values for semicircle, for quadricircle, and for ellipse. So these are the simple shapes you know the area moment of inertia values for. You know moment of inertia values for moment of inertia about different axes. Your goal is use this table and parallel axis theorem to calculate the area moment of inertia for composite areas. I'll see how do we do that. All right. Now, similar to finding the centroid of an area, you can estimate or you can form the shape of a composite area by adding two of these together or by subtracting two of these, right? Depends on what the area is. If you have something like this and you want to find the area moment of inertia for that, well, let me put it here like this. In that case, you will just break it into two rectangles like this and two segments. You know the area moment of inertia for each, sum them up. Or you could just do it in a different way, right? You might come to me and say, well, you know what, I want to break it this way. And then this would be one or two, and then find, so you add them up. This same area could have some rectangle shape cutout. Your area could be this. Then you would have done something similar to that. Maybe one segment here, one, this whole thing. Add these up minus the cutout part. So using these simple shapes, you should be able to form that composite area, and depending on it's a cutout or it's these areas added together, you end up adding those areas moment of inertia together to find the area moment of inertia for the composite area, or different kind of algebraic sum, as we mentioned here all the way at the beginning, right? We said composite area about an axis can be found by algebraic sum of the moments of inertia of all these parts. So if it's a cutout, you subtract it. If it's just adding two simple shapes to form the composite area, just add. All right.